Module 2.4, Applications of Density Functional Theory in Mechanical Engineering. In this module, we're going to learn how to install a density functional theory such as GPAW, run an example for aluminum, especially how to input aluminum atomic structure, how to visualize atomic structures, which could be important, and not just the structure, the optimization and other outputs as well. Run structure optimization of aluminum, analyze properties such as electronic density of states, electronic band structure, charge densities, generate stress strain curves, which you might have heard in your undergrad course and so on, and which could be very important for mechanical engineering applications. Calculate elastic constant and bulk modulus. So let's be fair. Quantum mechanics is difficult. All the stuff that we went through in last couple of modules could be quite overwhelming. Too much maths, too much counterintuitive stuff. But I want to point out it is important. And when you specialists try to simulate materials at a very small scale, there is no other way than to simulate with quantum mechanics. However, as engineers, we do not want to go too much detail in maths, and we just want to solve engineering problems. And that would be our focus. So my goal here is to introduce to you these tools as something as a support when you try to understand or try to solve a mechanical engineering problem, especially when you are dealing with new materials or defective materials. And there are some phenomena that you cannot explain with finite element or molecular dynamics or any other higher scale method. Then you have to come down to quantum mechanics or density functional theory. So I think it's very important to be familiar with this, and especially as we learn through examples, things might become more clearer than going through all the equations and physics. So let's get into it. So let's start with aluminum as an example. So just as a general note, before you do any modeling of any material system, whether it's a metal, ceramic, polymer, or so on, it's important to understand uh, the applications and strength and limitation of that modeling methods. So here we are choosing aluminum because it's an extremely popular material for mechanical engineering application, and not just aluminum, their alloys could be very important as well. Aluminum is used in daily life, such as for automotive industry, for especially for weight reduction, and it can be used for different engine components, transmission, and so on. It's also used in construction industries. There are also marine engineering applications. So on your right-hand side, I show you a block of aluminum, very shiny, and on your left-hand side, I'll show you a bicycle part, which is composed of aluminum alloys, most probably. So let's start with DFT simulation of aluminum with GPAW. So again, there are many softwares out there, Quantum Espresso, VASP, but we're gonna just stick to GPAW because it's maybe easier to follow the examples. And there is an explicit example of aluminum on their website, which I have given the link here, so feel free to check it out. And on your right-hand side, I will show you Google Colab notebook snippet. So the idea is at the end of this module, you will be given the link to the Colab notebooks, something very similar to the previous module. And you can run these blocks, code blocks, one by one and see your output yourself. Change it if you want to, which could also be a part of your assignment. And let's get into this. So this is the official GPAW website on your left-hand side, and it's showing you how to construct aluminum structure, how to and other details that could be important for application for mechanical engineering and other application as well. But here in this particular session, we will learn about the mechanical properties of aluminum mainly, not too much about electronic or any other properties. So it may be a trivial task, but installing softwares for modeling, multi-scale modeling could be quite challenging. So I wanted to point out, although it seems like a trivial step, it's a very important step. So how do you install softwares? So it depends on what kind of operating system you're working on, Windows, Mac, Linux, and so on. So we are gonna work on here on Google Colab, which is based on a Linux system. And in Linux, if you want to install a software, we use apt-get install or apt install. So here we're installing Python and other GPaw data and so on. And once you've installed this, you can install Python packages using a very useful tool called pip. So you can do pip install blah blah blah, whatever package you want to install, and it will be installed very easily. So here we have installed GPaw and some other tools that might be necessary for this course. So yes. So anytime you want to work with a software, make sure that you understand their installation procedures. All right. So what's the input of a DFT calculation? As we mentioned in the previous module, the atomic structure can be described by a lattice constants, 3 by 3 matrix, element types, n by 1. So n is a number of atoms. So suppose you have 10 atoms in your system and all the 10 are aluminum, then your element type is all aluminum, of course. Or you might have alloys, then you have different type of elements and so on. Coordinates, this is the XYZ coordinates of the atoms, which is usually n by 3 matrix. On your left-hand side, I show you FCC aluminum in primitive cell. So as you can see, I'm trying to enter this in atomic structure information in the format something called postcard. So there are many ways you can input uh, the atomic structure information, but here we'll stick to the postcard format. So the postcard format, the first line is the my system. It can be any header. So it's just a common name. You can try to choose my system or aluminum or whatever you want to give. That's a header. Then 1 is a scaling factor. Usually it's 1. And then you can see a 3 by 3 matrix, 0, 2.025, 2.025, the next row and the next row and so on. So that is called lattice matrix that we talked about, 3 by 3. Next is the what type of element. So aluminum denoted by its symbol Al. How many of them? So 1, just below this. And direct coordinates, or there are different type of coordinate system, fractional coordinates, Cartesian coordinates. Let's not go into that, but just we will be working on direct coordinates and can specify aluminum Cartesian or fractional coordinates in 0, 0, 0, which is x and y and z coordinates. And on your right-hand side, I'm showing you how we talked about the lattice constant in the previous module. So this is how we typically input atomic structure in a DFT software. Now, I also wanted to point out there are different types of crystal structures, different types, something called space groups, point groups, crystal symmetry, and so on. We'll not go in detail of this, but I do want to point out that there are something called primitive atoms and conventional atoms. So primitive atoms or primitive atomic structure are basically the smallest number of atoms that can be the material can be reduced to. So here you can see aluminum is only one atom in the unit cell, and you can make a supercell or multiple cell or replica of it to make a supercell. And you can visualize right below the primitive atoms, the gray atoms, those are the primitive cell. And you can see because we do not have the lattice matrix in a diagonal elements, that is x, x, y, y, z, z components, these are a little bit rotated. Sometimes it can be useful for computational expense purposes, but may not be useful for understanding the structure. So on your right-hand side, I show you more conventional or standard way of showing aluminum. So you can see 4.05 angstrom is basically the lattice constant of aluminum, and it's given in the 1, 1, 2, 2, 3, 3 component of the lattice constant matrix. So that's what's represent. So and then in addition, we have 4 atoms in the conventional cell instead of 1 in the left-hand side. So hope it makes sense. So you can, the idea is basically using symmetry rules, you can convert the information from the right-hand side to the left-hand side and left-hand side to the right-hand side. So they are interchangeable in a way. So during our calculations, we'll be working on primitive atoms only because it has less number of atoms and easier to simulate. So now we knew the lattice constant of 4.05 angstrom. What if we did not know it? So in that case, we might need to optimize the lattice constant. And so let's assume we do not know it, and we give this atomic structure to GPaw to kind of optimize this for us. So GPaw also needs inputs, such as we discussed about the plane wave basis. So the PW on the left-hand side represent plane wave, and they are represented by a cutoff. So this cutoff is 500 electron volt. Let's assume that is our case, but sometimes it can be needed to be converged for a particular system as well. Different type of exchange correlation function we talked about. Let's assume PBE, which is the name of 3 scientists, and this is extremely popular and one of the highest cited papers in physics. And the k-point mesh is another variable, so we can take 666, 999, 11, 11, 11, so on. So here, as you increase k points, your computational cost will increase. So we're gonna just stick to 6 by 6 by 6. And as we show in the right-hand side, these are self-consistent run. So basically, it's based on a variational principle. You keep varying it until you reach the required accuracy. So here we define our accuracy in energy to P10 to minus 6, 1 E minus 6, charge density, accuracy 1 E minus 4, and so on. And then this calculator object called calc is given to aluminum, and we use something called BFGS. This is also the name of scientist. It's a way to optimize the atomic position. So basically, it will take a guess electronic charge density, then calculate the electronic density, and then from there calculate the wave functions, calculate the energy difference, and do it iteratively until it has converged. So after a few seconds of running the simulation, you can get a final atomic structure of aluminum. Now, atomic structure is definitely an output, converged atomic structure, but other important outputs are energy, forces, and stresses. So GPAW allows you something called aluminum. This is the atomic structure, dot get total energy. So aluminum here is just a variable, and dot get total energy is a function that we define in the first module of programming. So we got the total energy in minus 3.73 electron volt. You can get forces. So because there is only one atom, we get 1 by 3 matrix or a row vector. And similarly, we have the stresses, which is a 6 vector or 1 vector with 6 components. So in electron volt per angstrom cube, but we can convert this into GP or gigapascal if needed. Other outputs are electronic density of states. So calc, the calculator, also has something called get DOS or get density of states. They are spin up and spin down, denoted by spin 0 and spin up. So we're going to take spin 0 component only. And we can also get something called Fermi level. So you can subtract the energy minus EF Fermi energy and then plot it against the density of states, which is shown in the right-hand side. So here's the 0 is the Fermi level. So basically, it's showing you that there are states at the Fermi level. So this is a metal. If there are no states at the Fermi level, it will be an insulator, and so on. So yeah, states at the Fermi level play an important role. Another important quantity is electronic band structure. So electronic band structures are basically the how the momentum vary for electrons as they go through different parts of the unit cell in Brilliant zone. So here we'll not go in detail of this, but basically the idea is you can get a lot of electronic structure information from the band structure information, such as electronic effective mass, Fermi velocity of bands, and so on. We talked about electronic density. We can also plot it. So again, calc has something called get pseudo density, and you can plot it as a plotly object, as you can see here. So we can use matplotlib also to plot this, but here I'm using plotly, which provides a better graphic representation, which is shown on the right-hand side. Pretty nice looking, in my opinion. So here basically showing you that the red part is basically the core, and as we go away from the core, the value might decrease for electronic charge density. Now, those electronic properties may not be very important for mechanical engineers, but what could be important is stress strain curve, which you might have seen in your undergrad. So in this one, on your left-hand side, I show you we vary the strain from 0, that is no strain, to 0.5 strain with an interval of 0.05 increment. And then we make a for loop, and for each of these strain, I give this strain as C1 or sigma 1 1 or sigma x components. So stress is a 3 by 3 vector, sorry, a 3 by 3 matrix. So we give this here as this stress equals to I00. So we are basically giving the stress in the strain in the X component. So it'll be strain. Anyway, so then we calculate the stress and we append in a array called stresses, and we divide by units.gpa to convert from electron per angstrom cube to gigapascal. And the plots is shown on the right hand side. So you can see it's tried to behave elastically, but after a certain point, it may not be elastic anymore. The response may not be elastic and can have yielding and so on. But I want to point out there are many things to play here. So we are simulating this material at 0 Kelvin. So most of the engineering applications are not at 0 Kelvin. And also most of the engineering applications may have defects such as defects such as the atoms might be moving, a line of atoms might be moving, and so on. But here we are trying to simulate a perfect crystals. Okay, so there are a lot of assumptions here. So I might ask you in the assignment to vary the 0.05 strain to 0.01, so you'll have more number of points, and the curve on your right hand side might look more smoother than that. You can fit the elastic response in the stress strain curve to get elastic constant. So here we get the stress 1, stress minus 0, which is basically the stress at the first point and the second point and the first point. And then in this way, you can calculate the elastic constant, which we get as 88 GPa, and the experimental measurement is 107. So you can see it's a little bit off because we have not actually converged our K points, cutoff, and so on. So we are a little off from experiments, but it can be improved. Now, another important quantity is bulk modulus. So while stress strain curve and elastic constant could be directional, bulk modulus give you kind of a collective response of mechanical deformation. So here we calculate the bulk modulus using something called equation of state. So ASE and GPAW has a nice feature for this called calculate EOS, equation of state, which basically takes energy and forces at varying deformation of volume. So it basically expands and contracts the aluminum cell and fits the equation shown on the left-hand side. And fitting this equation, automatically you can get the B0, which is the bulk modulus. On the right-hand side, I show you the parabola that comes from fitting this volumetric strain of the data. So hopefully we learned about how to calculate optimum structure, elastic constant, and bulk modulus of aluminum. And the fun part is if you want to simulate another material, you can just enter any other material in terms of their atomic coordinates and calculate their properties. So this is very useful for, especially for R&D applications.